Welcome to this masterclass in the Cloud Virtual Summit for Juniper Networks. In this session, I'm going to talk about building a 100,000 server fabric the right way. So there are many different ways you can build 100,000 server fabrics, of course using different kinds of devices, using chassis devices, whatever the case might happen to be. Well, in this session, I'm just going to talk through some of the principles behind the way a hyperscaler might build it, why that they build it this way, and some of the reasoning behind it. We're going to start a little bit in an odd place, which is going to be with business agility. Now, you might not think about business agility impacting the way you build a data center fabric, but it definitely does. Normally, when we think about building devices with large-scale appliances, like chassis devices and stuff like that, what we find is there's an ongoing mismatch between the business requirements and what the network can support. So for instance, if your business kind of grows along this gray line, but your network, if you're building your network in appliance-sized capacity, what you'll find is it follows this more stepped line. So each one of these upward steps represents a modification in adding some major component of the network, like a new module or a new chassis or something like that. Now you'll notice that these gray areas are places where your business has been restricted from continuing to grow because the network is under the capacity required. On the other hand, you'll notice these big blank areas in here where the network can support way more than the business needs. In this case, you're just spending a lot of money on network gear that you really don't need to spend. So how do we deal with business agility? That's one of the questions we need to answer when we're trying to build a data center fabric. Now, another thing is that we need to think about something called data, and data gravity and data disruption. So if data can disrupt a market, it will disrupt the market. I can give you lots of examples of this, but I don't want to spend a lot of time on it. But a very simple example. There are large-scale delivery companies who've used data to disrupt the delivery process or the way that people deliver packages. This gave them a large advantage in the business side. So the data itself becomes important. So network support systems need to be able to support the collection, movement, and processing of data to create what I call data agility. This enables business agility, and also you need to think about how you protect the data. Quite often we think about protecting access to an application or to an appliance or something like that. In reality, we need to think about how to protect against data. Now, one of the critical elements of data agility is the concept of data gravity. So data gravity just means that when data is moved from one place to another, other data tends to want to move with it. Okay, so in this instance, for example, once I take data and I push it off of my on-premises network and into a cloud instance, then what happens is I tend to draw other data and applications with it, building a cycle of pulling data across. Now, why does that happen? If I think about it, I could have application A, B, and C. And say A, B, and C share two different databases, D and E. Now, when A moves from on-premises to the cloud, it's going to need to access D. But when it does so, this link now becomes longer and A's performance will suffer. So the natural inclination is to pull D to the same cloud instance that A is on. Once that happens, the connection between B and D, which is also accessing this data, becomes longer. So now the implication is I should move B as well. Once I've moved B, B uses E, and once E, now this link is very slow, so the general tendency is to move E to the same place that A is, and then C is using E as well. So you can see this kind of creates a domino effect. Another thing about data agility is what's called Kai-Fu Lee's virtuous cycle. Now here, in the virtuous cycle, what happens is the more data I have, the more I can do analysis to figure out how to capture the market. The more I capture the market, the more data I have. So these two play against each other. So how do I build these kinds of data agility and business agility into my network? Well, one thing we have always used as network engineers is very traditionally is a concept of layering. But I want to talk about layering in a different way. We normally think of layering as being something that you do in a hierarchical network design. In fact, I wrote a book a long time ago called Advanced IP Network Design, and after that, Optimal Routing Design. And those books are very much around hierarchical network design. Well, let's begin by asking, why should we even use layers? Well, this is a long quote from Alderson and Doyle in this paper right here that you can go look up if you want to. And what you'll find is they say that complexity is most succinctly discussed in terms of functionality and its robustness. So complexity in highly organized systems tends to arise primarily from design strategies designed to create robustness to uncertainty. All that quote means is we tend to build very complex systems in modules. So if you look at a WASP or a B, you will find that there are 3 primary modules. And in between these modules are very small connectors, a neck and a waist. These very small connectors carry information between them. In a sense, these are APIs or interaction surfaces. Now, these interaction surfaces allow the WASP or the WASP by design to carry or to control the information that's flowing between these physical modules. We're going to do the same thing in a network. And again, normally I would do this in a hierarchical network by having my access, my distribution, and my core, or my access and my core or my distribution, however the case might be. In a data center environment, I'm generally going to be working with a large flat network. I don't really have the hierarchy that I would normally have in a normal network. So how do I deal with this? What I do instead is I can build a hierarchy of layers that is moving up the stack in terms of control planes, applications, and policy and things like that. So here's what I'm showing you is I have my physical topology down here. This physical topology is connected to a network core that connects to campuses and etc. Sitting on top of this physical topology, I would have an underlay here, and we'll talk about a bit more about the components in just a minute. I'll have an overlay. The overlay does the DCI work using virtual network segments within and between these overlays. So this is kind of my layering. I have an underlay, an overlay, and then a controller, or some sort of system that is managing this whole mess. The underlay is the focus in this particular presentation. Now, if I think about the layers, one thing I can think about is I have 3 basic things I'm trying to solve in my network to make it work. I can say that I have topology, reachability, and policy. Now, there are other things, but let's just focus on these 3 things. In my underlay, what I want to do is really focus on topology and reachability. And my policy is going to be a very, very minor part of my underlay. In my overlay, I'm going to be splitting topology and reachability against policy. So the overlay, something like EVPN networks or EVPN over BGP, is going to allow me to manage my policy to some degree or another, but it's also going to have topology and reachability. Now, when I get up to orchestration or application overlay, I can actually call this my infrastructure overlay, and I can call this my application overlay. What I'm going to do is I'm going to move to focusing on policy, and the topology and reachability become very small parts. So again, let's focus a bit on underlay. So let's talk about business agility in the underlay. This is a pretty typical scale-up network design based on hierarchical networks, right? So what I do here is, let's say I have a bunch of information flowing out of this internet connection or out of the network core down to server G. As the application becomes more popular or more heavily used, what I need to do is I need to scale up the network by increasing the bandwidth and the capability of each one of these devices along the way. So this is basically a scale-up model, because what I'm doing is I'm increasing the scale of individual appliances along the way to make it larger. Now, another option is to do something called a scale-out model. But to get to the scale-out model, we have to look at something called a CLO fabric or a spine and leaf fabric. So let's begin our examination of CLO or spine and leaf fabrics with something called a stoger frame or a stoger frame. Now, the history of the stoger frame is quite entertaining. There was an undertaker who ran a small business and had a competitor in the same town. And every time somebody would call and pick up and say, "I just want to talk to the undertaker," the switchboard in the town was supposed to direct them to one of the two available undertakers. What happened was that his competitor's wife ran the switchboard. So he decided it needed to be automated in some way. So he developed this concept called a stoger frame with his brother, and they designed it and built it and started marketing it. Now, in a stoger frame, what you have is you have a series of switches, and each of these switches is a 1 out by 100 or 1 in by 100 out switch. So if I do this way, I can have 10 digits in each layer, and then I have 10 layers of digits, and then I have 3 layers. So each one of these switches represents 2 digits, 2 digits, and 2 digits. Hence you have the 6-digit phone number that we're all so familiar with. So this is a stoger frame. Now, if you look at these switches, they are very large and very difficult to produce, and it's very difficult to wire this. So sometime later, after the stoger frame became very popular and other things, they decided they would try using crossbar switches instead of those big, heavy stoger switches. Now, this was done by a man named CLOS, so this is called a CLO fabric. So essentially, all this does is it has a fixed number of inputs and a fixed number of outputs, and these are simple crossbar switches. And by building the same 3 frames or 3 stages, then you can make it where you get a lot of connectivity with this very simple switch device, and every switch device can be identical. So this is what we would call today a single skew fabric. Every device is identical to every other device, and these are very simple crossbar switches. Now, it's important to note in this that the circuit setup is unidirectional through this crossbar switch. Now, I can transfer this to the idea of a data network by building a CLO fabric. Now, there are a couple of things you've got to remember about this. First of all, a CLO fabric, when you talk about IP switching, is what is called folded. And this is because while traffic or circuit setup in a true CLO fabric, a 3-stage CLO fabric, is always unidirectional, in a packet switch network, it's bidirectional. Every link is bidirectional because the packets are being switched over those links. Now, another point is this is very scale out. If I want to add more devices to make this fabric larger, then what I have is I just keep adding spines. Now, my limiter to the fabric is going to be the number of ports on each one of these devices. That's going to limit my fabric. So the way this gets me to my scale out or my business agility is by having this capability of scaling out to a broader fabric, to a wider fabric. Now, what about data agility? We talked a little bit about data agility. Well, what's interesting is in a spine and leaf fabric, or a CLO fabric in this particular case is what we're illustrating here, every path between every pair of devices is exactly the same number of hops. This is really important because if I have the same number of hops, then what I have is I have the same amount of latency and delay so long as the fabric itself is not overloaded. So this means that most of my traffic can run across this way. Instead of running up and down the fabric, it's running right to left on the fabric. So all of our what's called north-south traffic is converted to east-west traffic. So let's talk about CLO scaling just a little bit. Here's a couple of 3 Juniper boxes you might use to build these CLO fabrics. You might use the QFX 5232C and then a 48Y. So in this case, for instance, I can say if I'm using a 32C with a 48Y leaf node, so if I go back up, these are my spines and these are my leaves. Now I always draw my 3-stage fabrics or 3-stage fabrics such that the leaves are on the outside. A lot of people draw them up and down with the spine on the top, and then they call this folded, and the leaves on the bottom. Folded really has two meanings here. It means either you've drawn it in a folded format, or it means that the traffic is bidirectional. So I tend to draw mine this way. It's just easier for me to see the fabric and understand how it converges. So you can see I can build several different sizes of fabrics here. Now what if I need something larger than like a 64C will give me? There's a couple of options here. One thing I can do is I can replace these spine boxes with a chassis device. This will give me, say, 192 ports or larger. That allows me to have only 4 spines, but it allows me to say if I had 192 ports on each one of those spines, I could have 192 leaf nodes, right? So this is one way that I could go about doing this. Now it's interesting because what happens is in these chassis boxes, these actually have an internal fabric that connect the line cards. So in this case, I'm actually building a 5-stage fabric. One of the stages is hidden inside these chassis devices, if I choose to use chassis devices. This is actually no longer a CLO. It's called a Benesh, and this is also called a rearrangeable. Benesh designed this as a rearrangeable CLO fabric. So this is a slightly different style of fabric. Now another option you can use here is to use a butterfly fabric. So a butterfly is not anything official. This is what I call it. Different people might call it different things, but I call it a butterfly. So out here, I have my top of racks or my leaf nodes. In here, I have my spines. In here, I either have my fabrics or my super spines. I tend to call these leaf, spine, and fabric nodes, or fab routers, or fab switches, as the case might happen to be. Now, one of the interesting things about this particular design is that I get pods out of it. So I have these logical pods that I can use to scale out. I don't just have to add individual devices. I can add an entire pod at once. Again, the scale of the butterfly is primarily determined by the number of ports available on these fabric routers. There is another way of drawing this fabric, which is to show it in this folded format. And a lot of people like to draw it this way. So these are my fabric routers. These are these spine routers. And then these are these top of rack switches. So you can kind of see the way that it folds like this. And you'll see this in a lot of literature that this is the way these are drawn. Let's talk about what type of scaling you can get out of this fabric. If I'm using 64 by 100 devices, like a 5200-64 port device, what I can get to is I can get from 8,192 to 131,000 25 gig ports. Now these are 100 gig devices that I'm talking about. So what I would typically do here is I would use a 100 to 25 gig optical splitter or DAC. You could use a DAC as well here to split out my 100 gig. Note that the rest of my fabric, so what I have here, is, just to show you again, is I have 100 gig ports down here that I'm splitting out into 25 gig. Everything in the rest of the fabric is all 100 gig. This allows me to do one-to-one oversubscription in the fabric if I want to. Now let's just talk for a second about the underlay routing protocol, right? I have a lot of different choices here. I could use BGP. Now BGP tends to be slower convergence. I tend to have a hard time making BGP converge in less than about a second, or in some cases in minutes. BGP is not really designed originally to be very autonomic, so you tend to need to do a lot of automation. You don't have a lot of, well, you have a lot of telemetry, but you don't have what I consider to be very important, which is a link state database, which is an entire overview of the entire fabric. I also consider BGP to be fairly complex as a protocol. It takes a lot of work to make BGP converge at all in a large-scale fabric, or to converge very quickly. You can do ISIS or ISIS modified. This is what I would consider moderate scale. I've seen this up to 2,600 devices, or a fabric with 2,600 routers in it, and pushing about 120,000 routes. So this is moderate scale. It's much, much faster convergence. It's more autonomic. You can actually run ISIS almost autonomic. You need to configure just a couple of things. You do get your LSDB. You also get in near real-time changes in the network topology based on getting link state updates. And I consider configuration here to be a little bit less complex. There's also Rift, which is very large scale. This is targeting millions of devices in the fabric, or millions of edge ports. It's very fast convergence. It's actually faster than ISIS, or it should be. It's more autonomic. You still have your LSDB at some points in the network, and I consider it moderately complex. Now, of course, you could also run OSPF in these fabrics if you wanted to, especially in a smaller fabric. Now, when I talk about Rift and ISIS and OSPF, particularly ISIS and OSPF, I'm not looking at running multiple areas or multiple flooding domains. I'm talking about single flooding domain implementations here. So in ISIS, you would have a single L2 flooding domain. In OSPF, everything would be in area 0. Now, in the overlay, you would typically run BGP EVPN, and you would either run VXLAN or MPLS. Now, what you would do here is VXLAN is less complex because you're only running a single transport level network in your network. If you're running VXLAN, you would run SRv6 or a newer thing called SRM6, which really isn't fully deployed or widely implemented at this point. Now, you could run SRMPLS for traffic engineering, but that is going to be more complex. So, as one final thing, let's just talk about external connectivity. When a lot of people draw their fabrics with the spine on the top, and they say it's 2-stage, which it's really not, it's actually 3-stage, or they say it's 3-stage and it's not, it's really 5-stage. The number of stages is the number of devices to communicate between, that you have to cross in order to communicate between the farthest edges on the network. So this is a 5-stage, it's not a 3-stage. A lot of people will want to, when they draw things up here, or in a collapsed spine design, they will want to put their external connectivity on these spine boxes. Now, there are a number of reasons you really shouldn't do this in this kind of design. It's okay in a smaller design, of course. Say that you know for a fact you're never going to have more than 2 spine switches or 4 spine switches. Well, that's okay. And you don't want to buy a lot of big boxes to make this, to do the edge of the fabric capability. So that's okay. Now, of course, if you have 4 spine boxes that are your leaf or that are your border for the fabric, and you only have, say, 2 internet connections, now you've unbalanced the traffic across these 2 spine boxes, leaving these 2 out. So you need to be very careful if you do this about the way you balance your traffic out and the impact you're having on the traffic flows through the network. Now, one other thing is say that you start with these 4 and you have 4 internet connections, or even say you start with 2 and you have 2 internet connections. Now you add a 3rd and 4th in order to scale out. Now as you scale out, you're unbalancing your traffic again. And you're also buying big chassis boxes to do the scale out. So normally in a chassis, if you're putting chassis boxes in here, you're going to do kind of a hybrid scale out, scale up situation, where you are adding line cards to the chassis rather than adding individual devices to do a true scale out. So that's kind of the thought. Normally what you would do is you would set up some part of your fabric that is your border leaf, and these would become your border leaf nodes. And because most of your traffic is being converted, or all of your traffic in a spine and leaf is being converted to east and west flows, every device on the network has, or on the fabric, has the same access to the external connectivity. All right, so let's just do a quick review and just talk a little bit about what we just talked about, just so you get it set in your head. First of all, business agility. How am I solving business agility? I'm using a scale-out network architecture. I'm using an overlay across all domains, cloud, edge, on-premises. This would be my EVPN overlay. and I'm paying very close attention to what's automatable versus what is autonomic. I want to make as many of these layers as possible, as close to autonomic as I can, or self-driving. And then I also want to make everything very, very automatable with machine interfaces. So I make everything very automatable. How am I solving data agility? I'm optimizing traffic flow costs by interacting with data gravity. I'm paying very close attention to where the data is, either in which data center fabric, if I have multiple fabrics, or in public or private cloud, or whatever the case might be. So this is how I'm going to do data agility. I'm going to reduce barriers to applications working with data, because what I'm going to do is I'm going to have that fixed length path across these spine and leaf fabrics that's going to allow the application to be tuned to operate on that path length. So that's going to be very important. For protection, each layer in this layered cake or this layered design can be independently secured. Furthermore, each layer can provide unique telemetry so you can see where data is flowing and you can correlate what's going on in the layers. So I hope that all makes sense and is useful, but this is some thoughts on how to build 100K fabric or how to build larger scale fabrics like hyperscalers do. Not saying that these principles don't apply to smaller fabrics, by the way. I think it's very important to pay very close attention to the way you're building things modular-wise and how they work. Look forward to having some live webinars on these same topics coming up in the future at juniper.net. Thanks for listening.